Okay, so last time we have been talking about the second order ODE, right? So in particular, the second order linear ODE, right? So second order linear homogeneous ODE, right? So, and then we know that for that kind of ODE, right? So we will be able to find out two linearly independent solutions, right? So, and the general solution will be a linear combination of the two linearly independent solutions, right? And in particular, right, so we have a very simple recipe to solve for the case when all the coefficient functions in the second order ODE are constant, right? So this type of ODE. And then the idea is that we assume that, right, so the solution takes the form, right, of this exponential function. And then the job becomes just finding R, right? So once you find the R, appropriate value of R, that can solve this ODE, right? Then you are done. And then therefore, right, solving this differential equation is just equivalent to, right, solving this quadratic equation, which is known as the auxiliary equation, right? So all you need to do, right, is to find out the two possible value of R, right, and then put it back to this e to the Rx, and then a linear combination of the two solutions is the general solution. So here, let me just do a couple of very simple examples, okay, just to make sure that we know how to use this method, right? So for example, if I have this equation, so 2 times d squared y dx squared minus 5 dy dx minus 3y equals 0. So how do we do it, right? So we just need to write down the auxiliary equation, right? Auxiliary equation is this form, right? So 2 times, so this second order derivative terms, right, corresponding to R squared term, right? So and then this first order derivative, right, corresponding to a linear term R, and then minus 3 equals 0. Right, so our job is just to solve for R, right? So and then this one, right? So this quadratic equation, right? So you know that the solution, you'll be able to find that the solution is R equals to minus 1/2 or 3. Okay. So then that means, right? So your solution, general solution is equals to C1 e to the first solution minus 1/2 x plus C2 times e to the 3x. Right. So that's it. So then another case. So let me. This time I have d squared y dx squared minus 10 dy dx plus 25y equals 0. So again, this time the auxiliary equation is, this time I have R squared, so minus 10 R plus 25 equals 0. And what you realize is that this is actually R minus 5 squared. So that means I have a repeated root this time, or double root. So R just equal to 5. And remember, for repeated roots, so there's a little bit of trick we need to do, right? So is that now the solution is given by y equals C1 e to the Rx of 5x, right? Plus C2. Also, I have this e to the 5x here, but I need to multiply by x. Right? So to only this way, you can make the two solutions, right? So to be linearly independent. Right? That's what we need. You always need two linearly independent solutions. Okay, so just one more. So now, okay, so this time the auxiliary equation is 4r squared plus 4r plus 17 equals 0. So this time we got complex root. Okay, you'll find that r is equals to -1/2 plus or minus 2i. So in this case, okay, remember if we have this complex root, okay, so the way we deal with it is that, okay, for the real part, okay, we still have this exponential term. Okay. But then for the imaginary part, okay, that will give us this cosine and sine term. So, right, so these three examples cover all three cases that we talked about last time. Okay. So then now we know how to find general solutions, right? So at least for this type of ODE. So now again, when we solve for physics problem, okay, so most of the time, okay, we don't just want the general solution, but instead, right, so we want that solution that is specifically corresponding to a physics situation. So which is an initial values problem. Okay, so the initial values problem, that means that after I find the general solution, right, with this C1 and C2 constants, right, so I want to also figure out the value of C1 and C2. Okay. So then this idea here, right, I think I mentioned it last time, right, so it's the same idea as what we had in the first order ODE, right? So, but in the first order ODE, right, so we still remember that you just give me one number, right, as that initial condition. But this time when we solve this second order ODE, right, so to actually determine these two constants, right, so you need to give me two numbers, so as the initial condition. So just like what I said last time, right, so if you solve the equation of motions from Newton's second law, so which is the second order differential equation, right? So and then you want to solve for the position of the particle as a function of time, right? So not only that you need to know this differential equation, right? You also need to give me specifically the initial position and the initial velocity. Right? So that's the two initial conditions that we have. So then mathematically in general, so that means what we are dealing with is this, right? So I have this second order ODE here, right? So and then I give you these two initial conditions. So that means the first one is that at some particular value of x naught, I tell you the value of y, which is y naught. And then also at that same value of x naught, okay, so I tell you the derivative of y at that point. And of course, okay, usually when we solve this differential equation, okay, we also will specify the interval of x. Okay, so that is for this equation to be valid, right? But in physics problem, okay, sometimes you just consider this interval to be from -infinity to infinity. Okay. So now, if I give you these initial conditions, so how do we figure out C1 and C2? Right, so that's actually straightforward, right? So you just put this value, right? So back to this equation. So this solution is something that you have. I assume that you have already found, right? So the general solution. To put this back to this solution, right? So you get an equation, and then you put this also back to this, you get another equation. So that is, I got two equations using these two numbers. And of course, I have two unknown constants. So two equations. Then of course you can solve for it, right? So it's just two linear equations. Right? So if I well, let me just write this set of two equations as this matrix form. Okay, so then I will write it in this way. Right. So and then how do you find C1 and C2? You just right, take the inverse of this matrix, so that the inverse is on the right hand side. Right. So and that actually tells us one thing here, is that so if I have the solution, a unique solution that exists, okay, and that is already guaranteed, right? So because in the last time I already mentioned earlier in this set of lecture notes, is that if I have linear second order ODE, right? So and if and all the functions behave nicely, and then if I also specify the initial conditions, then it's guaranteed that your solution is unique, right? So that's one theorem that I mentioned last time. So that means up to this point, okay, I already know that it's already guaranteed that there is a unique solution, and there is a unique solution. That means this C1 and C2 are uniquely defined. So that means this equation, this set of equation, has unique solution for C1 and C2. And when I say that, that is equivalent to say that this inverse exists. And this inverse exists, that means this determinant has to be non-zero. Right. So now let me rephrase it, right? So that is, okay, suppose if I know that there is a unique solution, right? So then that is equivalent to say that this determinant will have to be non-zero for some interval, for some values of x. Okay, so in my interval of interest, some value of x, that means x naught. Right? So and this determinant actually is known as the Wronskian, okay, or Wronskian determinant. So what does it tell us? So why do we need this? Okay, so here, okay, what I'm saying here is that what I just said in the last slide is that if y1 and y2, okay, so are linearly independent in the interval, then this Wronskian will be non-zero for some values of x, okay, belonging into this interval. So because well, y1 and y2 are linear independent is something that we already agreed, right? So a long time ago, right? So that one is no problem. So what I said in the last slide is that if these two are linear independent, then that means this one can non-zero for some value of x. But well, in the last slide, I didn't really say the opposite, right? Is that if the Wronskian is zero, is non-zero, okay, for these two functions, then these two functions are linear independent. So this is something I didn't really say, okay, but in fact that is also true, okay. Or I should more precisely say that this is always true. But for this side, it's almost always true. But let's say we don't really need to worry about this special case that this one is not true. Okay, so as long as as long as this y1 and y2 are two solutions, okay, so of your linear ODE, okay, so then this is also true. So then that means the Wronskian itself, okay, so can be used as a tool to test whether two functions are linearly independent or not. But of course, you might immediately ask, why do we need this? But last time I already gave you a very, very simple or trivial way to test whether the two functions are linear independent or not. Right? It's basically you look at the two functions, and if one is a scalar multiple of the other, then these two functions are linearly dependent. Right? Otherwise, they are linearly independent. Right? So that's very simple. But here I tell you another way to test whether the two functions are linearly independent. So first, at this point, you don't really know why you need this, okay? Because the first test that I showed you last time is so simple. Now, indeed, for these two functions only, okay, practically Wronskian is not really that much useful. However, okay, later we'll say a little bit about multiple or higher order ODEs, right? So where we will deal with more than two linearly independent functions. Okay. When you have three functions, when you have four functions that you want to test whether they are linearly independent or not, okay, Wronskian will become a useful tool. Okay, in that case. Okay, but that's something later. At least for now, let's just focus on, okay, so why this Wronskian, okay, being non-zero is equivalent to say that the two functions are not scalar multiples to each other. So then this is just a simple proof here, right? So as I said, what you learned previously to test whether the two functions are linearly independent, okay, is just see whether they are scalar multiples. Or in other words, that means you try to divide the two functions and then whether you see a constant or not, right? So if it is a constant, then it's linearly dependent. So if this ratio is indeed a constant, then that means if I take the derivative on both sides, then that means the derivative of this y2 divided by y1 is 0. Then if you do quotient rule, And you also just forget about the case where y1 becomes 0. Okay, just assume that y1 itself is not 0. Then now you conclude that y1 y2 prime minus y2 y1 prime is 0. And this y1 y2 prime minus y2 y1 prime is exactly this determinant. Okay. So then that proves that, right? So there are kind of two ways to test whether the two functions are linearly independent or not. First way, practically the easiest way, take the ratio, or you take the Wronskian. So here, I give you examples. Okay. So y1 is sine x, y2 is cosine x. So are these two functions linearly independent or not? Okay. Well, first of all, if you just divide them, right? So you clearly know that you don't get a constant, right? So that you know that they are linearly independent, okay, just by taking the ratio. But if we just try to do the Wronskian, okay, so what do we get? We actually try to do the Wronskian. Okay, so then y1 is sine of x, y2 is cosine of x, and this y1 prime, what is y1 prime? Y1 prime would be cosine of x, right? And then y2 prime would be minus sine of x. And then this would be minus sine square x minus cosine square, and that is minus 1. So this is non-zero. So that it shows that these two functions are linearly independent. So so this Wronskian, so all you need to know is this form, right? So this is not very difficult to remember, okay? But although, as I said, at this point you might not feel that why is it so necessary to do this to test the linear independence. But I would say, when I say the higher order ODE, so I will come back to this. So before we move on to the next part, okay, so first let me give you one physics example. So that involves the second order homogeneous linear ODE. Okay. So this is a simple harmonic oscillator with damping. Okay, so I actually assume that you have seen this physical problem before. Am I right? Have you seen this physics problem before? Okay, so then you probably know why you have this equation of motion. Okay. But here I just want to discuss how to solve it, right? How to solve it. So maybe when you learn this problem in the physics class, they did not focus on how to systematically solve this differential equation, right? So here, okay, so I have this differential equation. I just treat it as a mathematical practice problem. Okay, so then what do I need to do? Right, so I need to find the auxiliary equation. Right, so auxiliary equation is this one. Okay. So now, if I go to find the root, okay, so then this is my solution, my root. Okay, and then this, I define this alpha divided by 2 to the gamma. Okay. So that if you simplify it, you will get this number. Okay, okay, but this is only for the case where, this is actually only for the case where omega not greater than gamma. So if you, actually there are two more different cases that we'll talk about. If you have omega not equals to gamma, right? So then R would just be minus alpha divided by 2. And also, one more case is that if omega naught is smaller than gamma, then what you have is R equals minus. Hold on. This one is wrong. So this is, sorry, this is a typo. So this is no square here. Okay, no square here. So okay. So then the second case I had is that this R is just minus gamma. Okay. So finally, okay, the last case is that this is minus gamma, okay, plus or minus gamma square minus omega naught square. Okay, so all three cases listed here. So then for three different cases, right? So you have the solutions, okay, behave differently. Right, so the first case, the omega naught square greater than gamma square, right, where you have the complex root, then your solution will look like this exponentially decay, okay, with this sinusoidal curve. And then for the second case, where omega naught square equals to gamma square, so that means you have this so-called the double root or repeated root, then your solution looks like this. So finally, okay, if you have this omega naught square smaller than gamma square, so then so this is just a real number now. The whole thing is a real number, not a complex number. Then your solution is also just a pure exponential function, okay, without the sine and cosine. And I believe that you have seen the different physical meaning of these three cases, right? So it's the so-called under damping, critical damping, and this over damping. Okay, where I plot all three cases here. So under damping is that the overall the position of this particle as a function of time, okay, is exponential decaying, but also is oscillating. So then it's this case here. Keep oscillating, but the amplitude of the oscillation decay over time. Then for the other two cases, right, so you don't, you just have the decay. So you don't have this sine cosine oscillation. So now, so that's pretty much about the so-called homogeneous linear ODE, right? So the homogeneous ODE, that means the right-hand side is 0, right? So now we will consider a slightly more complicated case where we have some non-zero function on the right-hand side. So for that case, okay, so the general solution can actually be written as a sum of two parts. Okay, a sum of two parts, and the first part, this blue one, okay, is known as the complementary solution. Okay. So this solution here in blue, you can see that is exactly the same as what I have here. Okay. So that means this part is just the solution of this equation, but with the right-hand side to be 0. However, okay, so I still have one more term behind. So this is known as the particular solution. So this particular solution really is a solution of this whole equation. Okay, it's a solution of this whole equation. So now you need to be careful about the difference between this YC and YP. So when I separate this YC and YP, right? So I require that, okay, this YP and this YC are linearly independent. So that means if this is my YC, this is something e to the R2x. And if my YP, if the YP that you found is also e to the R2x, then that is not considered to be a particular solution, because that would be linearly dependent, okay, with these YC itself. So when you find this particular solution, okay, make sure that it is linearly independent with this YC. So then what this GX could be, right? So it could be anything, right? So and whether we can solve it really depends on what GX we have on the right hand side, right? So if it is too complicated, okay, might not be able to solve it. So then what is the strategy? Okay, so it really depends on what you put on the right hand side. Okay, so I'll give you examples, but some common problem that you have seen is, for example, g of x that's equals to a constant, let's say, just equals to a constant a naught. Then what is the particular solution? Then the particular solution has the form of also a constant. Okay. For example, alpha naught. So if your GX is slightly more complicated, that is, for example, if your GX is a naught plus a1x, then the particular solution will take this form. Okay. So now what is your job? Your job is actually try the form of the particular solution, right? And figure out the values of alpha that can satisfy this equation itself. Okay. So that means the way to find the YP is again putting in a so-called trial solution, and then you figure out what are the constant values in the trial solution can satisfy your differential equation. Okay. So then more types that you'll see. Okay, for example, if you see that g of x is let's say a naught e to the kx, okay, then your trial solution would be this one. So you can see that the solution that you are going to try, okay, in these cases are basically exactly the same as the form of the GX itself. Okay. So, and if you see that this is let's say is a sine omega x, okay, or a cosine omega x. Then the trial solution you will try is this. So basically, it's a case-by-case consideration, right? So you really need to look at what GX you have, then you pick the form that is appropriate. So these are just just memorize them. Okay, just memorize them. So there's and then by just doing one or a couple of example problems, you'll see how they work. So of course, okay, in general, okay, this can be GX can be even more complicated. Okay, so and then here I'll just give you this table. Okay, just give you this table for you to try, right? So if you in general, if this GX is a nth order polynomial, okay, so then your YPX that you're going to try is also n order polynomial. Okay, but your job is to find out all these constant coefficient of the polynomial itself. And then if it is a polynomial times exponential function, then what you're going to try is also a polynomial times an exponential function. Okay. And then if more complicated, polynomial times exponential, okay, times this sine cosine term, then this is the form that you're going to try. Okay, so for the particular solution. Okay. But usually, okay, of course, it won't be that many terms that complicated. Okay, usually these couple cases, okay, will be enough to cover what you'll be seeing most of the time. Okay. So here, note that if you have just even the GX, you only have sine x or only have cosine x. When you try for the particular solution, you need to have both sine and cosine. Okay. You need to assume that both exist first, and at the end you figure out whether one of the this coefficient alpha or beta is 0 or not. Okay, so okay, the best way to learn is to look at examples, of course. This is the first example I want to talk about. Okay. So what are the procedures? First, don't care about the right hand side, right? So don't care about the right hand side, and then solve for the complementary solution first. Right? So if you don't care about the right hand side, then you will obtain this auxiliary equation, and then you find that this is 3 or -1, and then this is the complementary solution. So that's the first step, right? And the second step is to find out the particular solution, right? So because g of x is 3 times e to the 2x, right? So that's why the form of the particular solution I'm going to try is also some constant times this exponential function. So now, if I assume that, then what I need to do is to figure out this a. Right. So how do I figure out this a? Is by direct substitution. Right. So basically, I put this particular solution, right, back to the equation itself, and then see what value of a can make these two sides to be equal to each other. Right. So if I just put this a e to the 2x to the left hand side, so take the derivatives, then at the end, okay, so you see that this is this one. Okay, so I actually need to let me try to do it. Okay, the left hand side, right? So what is the first term? So let me just write it. So you take the derivatives 2 times. So that means this is a times 4e to the 2x. Right? And then what about this one? So this is minus 2, okay, times a times 2e to the 2x. And then the third term is just minus 3 times a e to the 2x. So then these three terms, of course, what you do is to take the common factor out. The common factor is e to the 2x. And also a is also a common factor. Right? So a, and then what you have is just 4 minus 2 minus 3. So that is equals to minus a e to the 2x. Right. So this is what I have on the left hand side. So left hand side is minus a e to the 2x. And then right hand side is 3e to the 2x. So that means a I made a mistake here. A is actually not minus 1, right? So minus 3. Right, so a is minus 3, not minus 1. So then my particular solution, okay, my particular solution minus 3 e to the 2x. Let me check again, am I correct? No, okay, no, I was correct. Okay, actually, I made a mistake here. This is 2 times 2. Right, so this is the second one. The second term here is actually 4 also. So that means the left hand side is not just a times e to the 2x, it's minus 3a times e to the 2x. So minus 3a e to the 2x equals 3 times e to the 2x. Right, so that means a is minus 1. Yeah, that's correct. So a is minus 1. So that means this is my particular solution. Then the general solution. Then what is the general solution? General solution is just summing this complementary solution. Right, so with this particular solution. So now there's a second example. So this one is slightly more special, right? So again, let's follow the same procedure. Okay, first complementary solution. I just treat the right hand side to be 0, right? So and then write down the auxiliary equation. Okay. Then this time you find that complementary solution is this linear combination of these two exponential functions. So now we have a slight problem here, is that you can see that one of the complementary solution, one of the solution here is actually the same as my function on the right. Okay. So that means if I am going to use the same strategy as the last slide, that I let yp equals to some constant e to the minus x, then that is a problem, right? Because that means you are assuming that your yp is linearly dependent with one of the solution in your yc, right? Then that is not yp, okay? Because we require that the yp itself has to be linearly independent, okay, with this yc. So then the strategy is that when you see that, okay, so they are linearly dependent, then use the same old trick. You try to multiply your yp by a factor x, okay, so that you make this yp is no longer linearly independent with the yc, right? So xe to the x is not linearly dependent with this e to the x. Okay. So then with this, you are ready to try. right? So you try this YP as this form, and then you just put it, right? So again, to the left-hand side of the equation. So this is slightly more complicated because you have this x term in front. But anyway, it's just taking derivatives, right? So taking all the derivatives and equate it with the right-hand side, you will be able to find that a is -3 divided by 4. Then your particular solution is this one. Then general solution is this one and this one. Okay. So procedure is also quite very standard, right? So just look at the right-hand side, right? So and then write down the corresponding form of this YP to try, and then figure out the unknown constant. Okay, so let's take a break here. Okay, we can come back at 12:30.